Okay, so far we've been looking at changes in conditions. So you look at a gas, the temperature, the pressure, the volume, and then you change it. So you change the temperature or you change the volume. And we've been ignoring moles. So we've been ignoring the amount of gas that is there. So what I want to add now is moles. So we're going to look at a gas now, not just the pressure, the temperature, and the volume, but we're going to add to that moles. And so there is an equation that relates these four properties at a given condition, so at a particular conditions. If you know three of them, you can calculate the fourth. So as long as you know three of these, you can calculate the fourth. So if we know, pressure, temperature, volume, we know moles. There is one of these that we already know because we did some stoichiometry earlier in the year. We did some stoichiometry with gas volumes at STP, if you recall, and I'm sure you do. So STP takes care of temperature and pressure. And what we learned about that is 22.4 liters is equal to 1 mole of a gas. So there's the volume, and there's the moles. So we've already done this, essentially. And we're going to see in a second that there's a constant called the ideal gas constant, which is given the letter abbreviation R. So the symbol is R. And it relates the temperature, the pressure, the volume, and the moles. And it's equal to this constant in different units. And so that's where we're headed with this. So here we go. So it is called the ideal gas equation. And there are a few essentially conversions that you need to know how to do in order to solve this. And we've done them all already. So I can go through this pretty quickly. And I'm going to go through this pretty fast. And again, because we've already learned them all. And I think you'll find it to be a pretty easy review. The first one would be, in order to do these calculations, you must be able to convert from grams to moles. So to refresh your memory, grams to moles, we need molar mass. I have nitrogen. I have 3 hydrogens. I add those two together, and I get 17.03 grams per mole. And I know that you know how to do that. So we can set that up as a conversion. I have 115 grams of ammonia, 17.03 grams and 1 mole of ammonia. And I can take 115 and divide by the molar mass, 17, and I would get 6.75 moles. So the first thing you have to be able to do is, if you're given grams, you got to be able to calculate moles. And I'm confident that you can. The next thing that we should be able to do is convert to liters. Now, we could have a few different units to get to liters. One of them might be centimeters cubed. Now, the easy one is milliliters. We would move to get to liters, remember, 3 places to the left, or divide by 1,000. If it's centimeters cubed, we know that centimeters cubed and milliliters are the same. So it takes 1,000 centimeters cubed to equal 1 liter, and that would give us 0.800 liters in this case. So there was a conversion that we memorized. 1,000 centimeters cubed equals 1,000 milliliters equals 1 liter. And then the key one was the last one, because you're going to see that in this, and that was 1 decimeter cubed. So 1 decimeter cubed. So related to that, 4.75 or 57 decimeters cubed to liters, the answer would be 4.57 liters, because decimeters cubed and liters are equal. Or to use the conversion factor, 1 decimeter cubed equals 1 liter. So we could set it up as a dimensional analysis problem. All right, so that's the third one. So again, like I said, I'm going pretty quick because I think you know how to do these. 689 torr to atmospheres, 760 torr in 1 atmosphere. So we're using, our standard pressure values. Again, I'm sort of beating the dead horse here, but I know you know these. 1 atm and 101.3 kPa. So there's the 4 common ones used in chemistry, and the ones that we've been using all along. And again, we would use those as conversion factors. So now the reason I said you got to go to to atmospheres is because there are 2 different values for that R, or that ideal gas constant, that are common. One of them has atmospheres in it, and the other one has kilopascals in it. Now, there is one for torr, and I'm going to show you how to calculate that. But those are the 2 common ones that you'll normally see. So this is just another example of going to moles. 32 grams per mole, 16 times 2, so 56.5 grams, 32 grams in a mole, etc. So I'll let you calculate that. You get the idea. All right, so the other conversion then is Kelvin, because with all the ideal gas laws that we've been doing so far, we can never use Celsius. I've been telling you that all the time. So 273 plus 38, and we get 311. Okay. All right, so with all of those done, here we go. So the equation is right here. So you could copy that down. PV equals nRT. Hugely important equation. When your grandkids are studying chemistry, you could say, oh, I remember that. All right, so I'm going to go through each one of these because where the last problems we've been doing, if it was in, let's say, milliliters for the volume, as long as they were both in milliliters, the milliliters would cancel. Or if they were in atmospheres, or if they were in, Kelvin. As long as they were in the same units, they would cancel. But when we're solving PV equals nRT, it depends on the value of R, what unit we have. But this is the case. So if you're solving volume this time must be in liters. So you have to be able to get to liters, hence the practice problems I just did. Moles obviously has to be in moles. Temperature, just like before, has to be in Kelvin. So that takes care of V, that takes care of N and T. So the one that's left is P, the pressure. And the pressure units depend on the ideal gas constants units, R. If you put the pressure in atmospheres, then this is the value for R, 0.08206. So again, it's called the ideal gas constant. And if the pressure is in atmospheres, that's the value. If the pressure is in kilopascals, then it is 8.31. Now, this is not a unitless number. I'm just putting it here as an example. And like I said, there is one that you can do that would equal torr. And you could find that very easily. Just take one of these and convert them to torr. So if we take 8.31, for example, and we want to convert it from kilopascals to torr, we would do 101.3, 760 torr, and we could figure out what it would be equal to in torr. So we could say 8.31 times 760 divided by 101.3. And you can see it's 62.3 if you had torr. But, like I said, these are the two common ones you'll see. I'm only going to give you those two. If you want to use one in torr, you most certainly can figure it out. But you could also convert the pressures to atmospheres or kPa. All right, so now the units for R are not really that important to remember, again, because I'm going to give you the ideal gas constant, so they will show up on your test when I tell you what R equals. Just know that if you're solving for volume, it's going to be liters. If you're solving for temperature, it's going to be Kelvin. If you're solving for moles, it's going to be moles. And if you're solving for the pressure, it depends on which of those two units, or which of those two R values you used. One of them will be ATMs and one of them will be kPa. Here are the official units, though. So if you have 8.31, it is equal to kilopascal liters per or over mole Kelvin. See, kilopascals liters divided by moles and Kelvin. So that would be moles and Kelvin over there, so divided by. Or it could be atmospheres liters. See, atmospheres liters per mole Kelvin. So depending on the pressure unit you use, you'll be using a particular value for R. All right, let's just jump right in and try it. All right, now notice a difference this time. In the previous problems, there was a change occurring. It changed. The temperature went up. The temperature went down. The volume changed. The pressure changed. Something changed. On these problems, you are at a particular set of conditions. Our conditions are not changing, but you're at a particular set of conditions. So, what is the volume? So we know V. Or we're looking for V. Sorry, what is the volume? Question mark. 7.50 moles, so that's N. Temperature, just like before, we want to add 273 to that, and we get 368 K, so T is 368 K. And then kPa, so 1P would be 108 kPa. So you can see we have the four conditions. We have three of them. Just like I said in the beginning, as long as you have three of them, you can solve for the fourth one. How? PV equals nRT. Plug them in. We have the pressure, 108 kPa. We have the volume. No, we don't. We're looking for it. We have the moles. Yep, 7.50. I'm running out of space. R. Now, R value. This is in kPa. When you're in kPa, R equals 8.31. Again, I say, don't worry so much about the units, because just know that they're there, and we're solving for volume, so our final answer is going to be in liters, because volume has to be in liters. But if you want to solve with the units, you most certainly come and change color so you can see it here. And then our temperature is 368. Okay. All right, so I'm going to solve for V. So I have that, times divided by that, and I get my answer in liters. So I'm going to do 7.5 times 8.31 times 368 divided by 108, and I got 212. So I have 212 liters for the volume of that gas at those particular conditions. Again, we're at a particular set of conditions. We have the volume. We have grams, so we can find moles. We have millimeters of mercury, so we have the pressure. And this time we're looking for T, the temperature. All right, so the centimeters cubed. So I have to get 750 centimeters cubed to liters. There are 1,000 centimeters cubed in a liter, because a centimeter cubed and a milliliter are the same. So I'm going to move it over 1, 2, 3, or divide by 1,000. So 0.7500 liters. Mass, 65.5 grams. I can't do grams, I have to do moles. So I have grams of I2. So I need the molar mass of I2, 254 grams in 1 mole. 127 is I times 2. And I now have moles, 65.5 divided by 254. So 0.258 moles of I2. My pressure, now it's in millimeters of mercury. I had told you I'm not going to give you a value for millimeters of mercury. I'm going to give you kPa or ATMs. So 760 millimeters of mercury. Since the last one we used 8.31, this time I'll go to atmospheres, just to show you it doesn't matter which one. 790 divided by 760, and I get 1.04 ATMs. So I have the volume, I have the moles, I have the pressure. So again, I'm going to be able to solve PV equals nRT using the ideal gas constant. Let me get rid of my title there, and I'll do it right up top. So PV equals nRT, the pressure. I calculated it to be 1.04 atmospheres. The volume, I calculated it to be 0.7500 liters. Moles, 0.258 moles. R, now R will be determined again by the units of the pressure, so 0.08206 is the units, or the value of R when you have atmospheres. And then T is temperature, that's what we're solving for. So a little algebra, multiply these two together, divide by those on the other side, and that will give us the answer in Kelvin, because it's a temperature. So 1.04 times 0.75 divided by 0.258 divided by 0.08206. And I get 36.8 Kelvin. Now if I ask for degrees C, we know how to do that. We would subtract 273 to go from Kelvin to Celsius. So that's PV equals nRT in a nutshell. From there, I mean, we're just going to solve for different units. So in this case, we're solving for the pressure. We have N2 and we have mass, so we can find moles. We have milliliters, so we can find liters. We have degrees Celsius, so we can find Kelvin. So we have the volume, we have the moles, we have the temperature, and we're asked to find the pressure. Notice it says the pressure in atmospheres, so we would want to use the value of R in atmospheres. One more. The volume, so we're looking for V. Grams of O2, we could find moles. Temperature, degrees C, we can do Kelvin. It's already in kPa, so we would use 8.31. So again, we have the volume, we have the moles, we have the temperature. So we have those three, we have the pressure, the temperature, and the moles, and we would be finding volume. It would be in liters, and we would just have to change it to milliliters. So that, in a nutshell, is PV equals nRT. And I'm going to stop there, and I'd like you to try these three. And then play the next video. It'll have the answers to these, and then I'm going to show you that there are two more equations dealing with PV equals nRT.